tyFlow Basics, Custom Properties Operator explained in detail tutorial. Enjoy. This short video is a fairly typical custom properties animation from tyFlow. Before we get into the nitty-gritty of the custom properties operator, I feel we need to touch on two other subjects. One is the timing rollout here, and the other is the display data operator. And the reason that we need to touch on those is the timing affects how we save or get our data, and the display data helps us evaluate what's being saved or what's being gotten. We can look at the actual matrix data. Before we get into deep explanation, let's just give an overview of this basic flow that was created for the purpose of showing how tyFlow data is saved and how timing and stuff affects it. So on this basic flow here, we're going to create a single particle and we're going to birth it on frame 1. We're going to position our particle on the icon and we're going to shoot it out along the icon arrow. We're going to give it a 3D shape so we can easily see it and follow it. We're also going to display both current and saved data so we can see what is being saved and what is being returned. Later, as we go through the tutorial, we're going to mess with the rotation operator and look at our matrix data. We're going to do the same for the scale, and we're also going to look at two different sets of saved data and how that happens in tyFlow. Let's quickly look at the display data operator and what we're saving in our flow. So here's our display data, and if we kind of look at the two sections here, basic data and custom data. Up here I am saving the transformation matrix data, which is everything about an object in Max, and I am also saving a custom float value, and it's being saved into a file here that I've called my current value. And if we go to Max for a minute so we can just see how that looks, and we scroll our timeline forward a little bit, you can see here this is our particle and these are our two custom or display datas that are being shown. One is the transformation matrix, which is everything about the particle being shown, and the other is our custom float value. So let's go into the whole transformation matrix and display data a little bit more in depth. Birth one particle, frame 1, one particle only at frame 1. When we look at our display data here, which is being shown in this section here, we can see that we are saving the two values that we requested. The transformation matrix data about our particle, and it's broken into these 4 bracketed segments called matrix data, which we'll explain in detail in a second. The first bracketed set is X data. The second bracketed set is Y data. Third bracketed set is Z data, and the last bracketed set here is X, Y, and Z position information. So our particle is 0.63 in the X, 0 in the Y, and 0.77 in the Z. Then we also asked to save a float value in a file called my current value, and that's showing 0. So, and that is supposed to be saving the magnitude of the particle. Now we can see here that our particle is at frame 1, but the value being saved is 0. So now we can already see the benefit of using display data to learn what's happening. If we scroll through our timeline on Max a little bit, right, you can see that on frame 2, what got saved to our file was 0.99, which was the magnitude, the distance from the origin the particle is at frame 1. And if we scroll forward again, you can see that the next value being saved is 1.99, which was the magnitude at frame 2. So already from this little exercise here, we've learned that the data that's being saved is last frame's data, and that only one value is saved. It's always being overridden. In our first custom properties operator here, we can see that we've set the timing to continuous, which means every time we advance a frame, the data in the file called my current value will be updated, and it'll be updated with the position magnitude information. So looking at our flow here, we've centered the position icon on the origin. So the data is starting at the origin, or the particle's first position is at the origin, and then at the end of each frame we update the value of the magnitude at the end of each frame, so it's constantly updating the distance from the origin, in this case, to the center of our particle. And if we step through max, we can prove that, and we can see here 0, last frame's value, 1.99, 0.99, 1.99, and it's constantly being updated as we advance forward with our frames. And that'll keep happening until the custom properties operator is no longer being evaluated, like if we leave the event or some other thing like that, or the timing is no longer valid. So if we go back into our timing here and now set that to event entry, you can see here that our value is now 0, because event entry is when the event is first evaluated at the beginning, which is actually before frame 1. So when we see our value, it stays at 0 and never updates. And if we go in and say on event age, and now we have 2 frames, 0, 1, and 2, which is actually 3 frames for real, but if we go back to 0, you'll see now when we step through max, we got the original value 0, and then on frame 1, frame 2, it's updated 0.99, and then finally it's updated to 1.11, and then it never updates anymore, because we've only asked it to save at the end of frame 0, 1, and 2. So that is probably enough coverage of the timing operator to give you an idea of what impact it has on the data being saved. So with that, we'll go back and finish our conversation on the transformation matrix, and we'll go a little bit deeper than we need to, but it's probably handy information to know. Okay, the matrix. What is it? And it ain't Keanu Reeves. So if we look here, this is the matrix data, TM or matrix 3 data. And remember what I said earlier, the first bracket is set was X data, the second bracket it said was Y, the last bracket, or second last bracket it said was Z, and then finally the fourth bracket was X, Y, and Z position information. And if I scroll through on a little animation I've created out here, and we look at what that means, generally speaking in computer graphics, most matrix data is in a 4x4 matrix, and that's a lot to do with when you do matrix maths. In Max, we basically drop this last set here and you never see it, which is again just for the purposes of matrix maths. And generally speaking, when you see a matrix, this is what a matrix looks like as far as computer graphics, mathematics. And when we scroll through a bit further and we see what tyFlow matrix data looks like, which we've already kind of covered earlier. Now, again, this is just position information. For knowledge, everything in this top 3 brackets here holds information about everything about a particle. I mean everything: skew, angle, position, rotation, you name it. Maths geniuses somewhere have figured out how to fit all that information into this little tiny matrix. So if we go further forward and just look at that like that, you can see here that if you messed with these 3 values, you would be messing with scale. So, and it's not exclusive to scale, because if we look over here, some of those same values are being used in rotation, so it could be a combination thereof. We don't really need to know this stuff, but at least if we have some idea of what we're looking at when we look at display data, and we have a little understanding of the matrix, then we can understand what we're saving, what we're using much better. If we delete this here and go back to our original window here, and we now go in and put our particle somewhere here where we can see it, and we can see the data here. If we now go into this scale operator and enable it, and we can see that we've set the X, Y, and Z, or the X and Y to 200%, but the Z has been left alone. And when we look at that matrix data here, we can see now instead of a 1 for X and Y, there's a 2, and Z still has the 1 value. So you can see right there how scale, changing the scale, affected those values. And if we now add the rotation operator to the mix, you can see that I've rotated the y-axis 45 degrees, and we can see how that really changed our display data here, our matrix data. And you can see that now there's some mathematical genius going on here to explain what's going on with our particle. But again, this is just to reaffirm that every single thing about this particle is stored in this matrix data. I think as far as what we need to know for tyFlow, that's probably enough about the matrix. So let's talk a little bit about our custom properties here, and what exactly does float, vector, and TM data mean. So let's just explain these 3 values here and what they mean. Float, vector, and matrix data. Why is it named that? Well, it probably comes from computer mathematics, right? And Tyson being a maths genius and a computer programming genius, that probably makes sense. Float. Well, float equals a decimal value, right? So that's like in computer maths or whatever, you have a float, an integer, and a double, and all those kind of values. Well, a float contains a decimal number. It could be 1, it could be 1.5, it could be 1.141957, whatever. So that's a float value. And when we look over here and we see our float choices in this drop down here, we can see things like position X, Y, and Z, or velocity, or magnitude, or any other number of things like materiality, event age, timing, etc. One thing these all have in common is they're single values. There's only one value being saved in a float data. Now when we go to vector, first of all, what is a vector? Well, a vector really is just a position in 3D space, right? So there's an important caveat to that, and that's it's got to kind of have magnitude and direction to have any meaning. So for example, if we roughly had, like our axis here, and we had a point in 3D space, and this would equal a vector, and if in this instance the reference point was the origin here, the vector would be, like the magnitude and direction to that point in 3D space. So from this point we can derive a vector. Now, a vector doesn't exclusively, for example, happen to have to originate from the origin. If we had another point in 3D space over here, we could have a vector from the first particle to our second particle. So that, for tyFlow purposes, kind of explains what a vector is. And when we look at the vector choices, we can see that they hold things like position, velocity, spin, scale, and that kind of stuff. It's not just a single value like a floating number. When we look at this TM data here, and there's a few choices in here which are kind of like combinations, position, rotation, scale, or position and rotation, and the other two here. But probably the one that people use the most is TM, which is, matrix 3 data. And TM data is really, like I've said, everything, like I said before, is everything about a particle, an object in max. So TM equals everything, and that's probably the one that most people use in that TM rollout. So if I save TM data, I'm saving, for example, if I split a sphere into multiple objects and then I had them all drop on the ground in little parts. Sorry, my drawing is rather pathetic, right? Then, everything about this split sphere, like rotation, position, size, everything about that would be saved. So for example, later, if I want to reassemble that broken sphere back into its original form, I can now animate that process and get it back exactly the way it was before we split the sphere. So, most people, I think, when they're using TM data here, will end up using this, which is everything. And maybe for some select animation scenarios, you would choose to filter it down to more specific information. So I hope that at least explains a little bit about why we call these things float, vector, and TM data. So let's move on to talking about all the different properties that we have in the custom operator. Let me delete this stuff and get rid of this. And the custom properties operator. is kind of broken into this display. It's fairly simple in a way, even though the diagram looks like quite a nightmare here. If we kind of look at this, this is the main rollout for the custom properties operator, and the choices that are in the operation are shown over here. The choices for the data source are shown over here. What kind of float values we can choose are shown over here. Interpolation, like how we're going to interpret the transition from as the animation occurs, is shown here. Our choices for vector data are shown here, and then finally TM data is shown right here. So essentially everything that is currently available in the custom property operator is shown on this screen. We've got the info rollout that just tells us what the custom operator does, and because the timing is important, the timing rollouts over here is included for information purposes. So let's go through some examples and explanation of each one of these items in the custom properties operator rollout. Let's look at the parameters here in the custom properties. Let me just set up an exclusion zone so I can access tyFlow. Okay, we're all set there. Alright, so in this operation here, we have, set and get, right? So obviously set equals saving data, right? And get equals loading data. And the data that you're getting or setting is whatever you've decided to do in these three rollouts. Now, it doesn't have to be a single choice. You're not limited to say just to set or save the float data. You may save float data and vector data and TM data, and later on you may load one or multiple during your animation time, and you save it into various files that you give a name. It would make sense that you give it something meaningful. And same here, if we go down here and write something meaningful, right, like my vector data, something like that. So that's your set and your save and your load features here. And in the data source, it can either be from within the flow, or you can target the information from a target particle, and same over here. Now, just about how this saving works, and we touched on it earlier, but let's say that we have a position icon and we spit out a particle, and it starts to drop because we've added gravity and all that, and down here somewhere we have our ground plane, right? And if each one of these corresponded to a frame number, and let's say so this would be frame 1, 2, 3, 4, etc., right? And let's say that we decided to save up to frame 4. That means that we would be saving the position here in the file. Now, that doesn't apply what's written over here, because I would have to actually have chosen the right one. And let's just change that and say custom vector, we're actually going to say position of the particle. So we stop saving here, right? This is the last save. And we let our animation carry on. At some point, we decide that we want to load that data and retrieve it. So what happened is, as the save is carrying on, it's not saving a history. So this whole trajectory isn't saved. Each time it saves a position, it overwrites the old. Now, if you have, 1 particle, or 100 particles, or 10,000 particles, that particular information will be saved for 1, 10, 100, whatever the number is. We're just using 1 because it's simple for explanation. So later on, if I say I'm going to retrieve that position and I'm going to animate my particle to go back, for example, what my particle will do is it's not going to follow this trajectory because there is no history. So that's not how my particle is going to travel. When I decide to retrieve it, it'll take a direct route from wherever the current position is to the saved position. So that just gives a little bit more explanation as to how data is saved. Now, the interpolation down here, right, that kind of, you can play with these values and these options here to decide how that happens. Like, if it's normal, it can be like boom, boom, 1 frame and it goes right back. And if you decrease this number here, it could take 20 frames to move back. And let's kind of look at a practical example of that in action. Before we move on to the practical example, let's just talk about the last couple of parameters. The uniqueness here is just a random kind of generator. It'll vary any flow that has any kind of randomness in it, for example, forces or rotation with variation or anything like that. Every time you change the seed, you essentially change the randomness part of it to be something different. So by changing the seed each time, you'll get a slightly different result on your flow. If we switch to our other custom properties operator we said earlier, which is actually set up for position X here, and we look at the multiplier and the value and variation here. Well, first we'll talk about the multiplier, and let's just zoom in so we can see it better. Right, so right now it's got a value of 1 and we're looking at position X, right? So if I multiply that by 10, you'll see that it changed what was stored in the custom float. Now, it didn't change the position of our particle because that's the reference value, but the multiplier takes that reference value and multiplies it by whatever you put in it. So later on, if you were to get that save value, you would multiply its location, position, rotation, whatever it is you're trying to save. Now, when we're looking at these two values here, they're grayed out because they're really meant to be for an exact value that you might type in. So if we go here and say by value, they become active. And now if we put 5 in there, and it's multiplied by 5, which must have been existing values, you see we get 25. If I put 1 in there, multiplied by 5, so this is a way for you to enter a value directly for whatever it is you want. And it would just be a hard-coded value that you put in. So I think with that, we'll go to that practical example we were talking about, in which case we'll also cover this interpolation section of the custom properties operator. I've created this basic flow to mimic what I drew on the screen earlier, and if we look here, we're birthing a single particle at frame 0, we are saving custom data in a file, and we're doing it based on particle age from 0 to 10. So when we look over here, we can see what I've written here is frame 10 should be the last position at which we save the data. And then it's pretty well like we explained, you know, shoot the particle out of an icon, give it shape, add some gravity so it starts to fall to the ground, give it some speed so it actually shoots out from the position icon. The collision test will turn on when we're doing the test, and then we got display data just separated into two separate lines. One is live data and the other one is custom save data. And if we go back here to our custom properties file and scroll down here, we'll see that we're not saving any float, we're not saving any vector, but we're saving position information into a file called my custom TM. So when we scroll through without the collision on, so the collision isn't on there, if we scroll through and just see that it mimics what's been drawn out in the graph, and without the collision test on, if we played the animation, it would just kind of fall through. Alright, so let's go back and we'll turn on our collision test for a minute, and now we see what happens. So we save data up to there, so this is the position of our particle at the saved time, and we scroll through until it collects with the ground. Boom, it just turned yellow, which means we jumped into this flow and we're stopping the particle. Now we're getting the data, and if you look here in the timing, it just says continuous, but you see that we are getting the position information and we're getting it from the file we saved earlier in the custom properties set, except now we're getting. And you can see here that I've set the interpolation value right here to 0.1. Originally by default it's 1 if we had default. So now when we play, we see, like I drew on my diagram earlier, the particle takes a direct line back and it should go back to frame 10. And you can see that the interpolation slowed it down by the number of frames. Now we can prove that by going back here and changing this to the default value of 1. Right? And now when we scroll forward until it hits the ground at frame 23 there. Now see what happened? On frame 24 it jumped back to the position. So it's an instantaneous jump. Alright, this is where interpolation comes into play. If I set it something to a value like 0.01, alright, now when we scroll through, it'll take a long time to get back. It may not even get back by the time we reach our 100th frame. In fact, it's not going to. So this will give you an idea of what interpolation does. Now if we had more than one particle, and like we had 10 particles or something, and we played with the variation, that would change slightly the duration of when the particles returned, right? And just give it a little bit so they don't all leave at the same time, arrive at the same time kind of thing. Maybe I can show that. Let's see if I can. If we go up here and let's put our time like back home for a minute. Alright. And say let's birth 10 particles, right? And now we're going to birth 10 particles, and you can see them all. We'll turn off the display data so we don't convolute our screen here, and we've got 10 particles coming down and they're all working back, right? And we'll also turn off this display data, and you can see they're all kind of coming back at the same time. So let's change our interpolation a little bit so it doesn't quite take so long. Let's do something like 0.08. Alright, and so now we're going to change the variation. Let's do something like 50%. And see how now all the particles are staggered, and even the way they act down there and how they return back just gives a little bit of randomness to it all. So, and that is most of the parameters in custom properties explained. Now obviously this practical example here is just a reinforcement of things we learned. It's not a fancy tutorial that you'll show all your friends. So I'll follow up with an actual real life example of using custom properties in action. One last important troubleshooting thing before we move on to a practical example, a real world example, is if you have a problem come up showing something like this, cache not available. I'll zoom in so you can see it better. You see right there where it says cache not available. That usually means that one of your options in your settings is not turned on. So if that happens for any of your data that you're saving or trying to view, then you just need to go over here into tyFlow settings, right, and go into cache and make sure I generally turn all these on when I'm playing with custom data, and you turn that back on and then you'll see that rectifies that problem. So just be aware, if you see that, this is where you fix it. That's it. This is the end. We'll do a real world project file as a separate video. See ya.